You clicked because you want to run large language models locally, and that is a valid goal. The problem is that most of us treat Inference as a simple library import, ignoring the massive performance bottlenecks created by standard Python runtimes. By the end of this video, you will understand why the future of local AI requires decoupling your compute engine from your language runtime, and how this architectural shift unlocks performance that current tools simply cannot match. Let us start by looking at how we typically approach local inference today. You install a Python package, load a model, and call a function. It feels seamless, but that seamlessness comes at a steep cost. The Python interpreter itself adds significant overhead, creating a barrier between your code and the raw silicon of your graphics processing unit or central processing unit. Every time you make a request, the runtime has to interpret your code, manage memory in a generic way, and handle garbage collection, all while waiting for the hardware to finish its calculations. This means your powerful machine is often idle, waiting for the software layer to catch up. The industry has been trying to solve this for years. We see projects like llm.cpp gaining traction because they move the heavy lifting into C and C++, bypassing the Python interpreter for the core inference loop. This is a step in the right direction. However, even these solutions often remain tightly coupled to specific hardware architectures or specific model formats. You are still bound by the limitations of the runtime environment you chose. If you want to switch from a consumer graphics card to a specialized accelerator, or if you need to push latency to the absolute minimum, the standard approach hits a wall. Here's the thing, the real breakthrough does not come from optimizing the Python code further. It comes from redefining what the boundary between software and hardware actually is. We need to look at how other industries have solved similar problems. Consider the world of high-frequency trading or scientific computing. They do not rely on general-purpose interpreters for their critical paths. They move the logic into firmware or specialized hardware where the code is compiled directly into the machine instructions that the processor executes. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is where the concept of decoupling becomes critical. Imagine you are building a house. In the traditional model, the foundation, the walls, and the roof are all poured as one solid block. If you want to change the foundation later, you have to tear down the entire structure. In the decoupled model, the foundation is a standardized interface. You can swap out the foundation for a stronger one without touching the walls above it. In the context of local inference, this means separating the compute engine from the language runtime. The language runtime, like Python, handles the orchestration, the API, and the user interaction. The compute engine handles the raw math, optimized specifically for the hardware it runs on. We have seen this work in other domains. There is a project called Conifer that demonstrates this principle perfectly, though not in the way you might expect. This is not a large language model runtime. It is a specialized runtime for boosted decision trees running on field programmable gate arrays. The project takes models written in standard libraries like scikit-learn or XGBoost and compiles them into FPGA firmware. This process translates the high-level logic into hardware instructions that run at the speed of light, bypassing the operating system and the interpreter entirely. The result is inference latency that is orders of magnitude faster than any software-only solution. Now, you might be wondering how this applies to large language models. The answer is that the architectural principle is the same, even if the specific project differs. The current landscape for local inference is dominated by tools like Inference, which offers unified APIs and auto-batching for models like llm and Qwen. These tools are excellent because they allow you to swap model backends by changing a single line of code, but they still rely on the underlying software stack to manage the compute. The true potential lies in pushing that boundary further. If we treat the compute engine as a distinct, swappable component, we can optimize it independently for specific workloads. We could have a compute engine that is hard-optimized for sparse matrix multiplication, another that is tuned for specific memory bandwidth constraints, and a third that leverages emerging neuromorphic architectures. The language runtime would simply send the request to the appropriate engine, and the engine would execute it without the overhead of interpretation. This decoupling changes the entire economics of running local AI. It means you are not limited by the performance of the language you write in. You are limited only by the hardware you have and the efficiency of the engine you choose. For a junior engineer, this is a crucial realization. You stop thinking about how to make your Python code run faster, and you start thinking about how to design systems where the hardware does the heavy lifting. Consider the implications for production environments. When you decouple the compute, you gain the ability to scale horizontally with much greater efficiency. You can deploy lightweight inference engines on edge devices where power and memory are scarce, while keeping the orchestration logic on a more powerful server. This separation of concerns allows for a level of flexibility that monolithic runtimes simply cannot provide. You are no longer locked into a specific vendor or a specific model format. The insight that ties this all together is that the future of local inference is not about better Python libraries. It is about better hardware abstraction. By treating the compute engine as a first-class citizen, distinct from the language runtime, we unlock performance that was previously impossible. We move from a world where software dictates hardware limits to a world where hardware capabilities drive software design. This shift is what will allow us to run complex, large-scale models on everyday devices with the speed and efficiency that our users demand. The path forward requires us to rethink how we build these systems. We need to move beyond the comfort of standard libraries and embrace a more modular, hardware-aware approach. It is a challenge, but it is the only way to truly redefine the hardware boundary for local LLMs. By adopting this mindset, you are not just writing code, you are designing the infrastructure for the next generation of artificial intelligence. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.